Hi, my name is Chad Orzel. I'm the professor who's going to be teaching the second module of Physics 100, and I'm recording this in late August. Now, my plan is very much to have the classes in person and do live lectures, but you know what they say, you should always hope for the best, plan for the worst. So I'm pre-recording these so I'll have something in hand should we need to go remote for whatever reason. This is also going to have the nice effect, I hope, of having these lectures recorded as a resource that you'll be able to use if you missed something or didn't get everything in class as we were going through it. I also intend to, in a couple of places, I'll go into a little more depth in these video lectures than I will in class, because I think some of what I'm going to say is going to be reviewed to some students, but not necessarily to everybody. So as a help to those who would have a little more confusion about the subject, or who would benefit from hearing it explained in a little more detail, I'll go into a little more detail on a couple of things in these video lectures than I will in class, where time constraints are more of an issue. When we do these live in class, they're going to be lectures that are about an hour in length. I'm not going to make hour-long videos here because nobody watches anything that's that long anymore. So I'm going to try to break these up into shorter pieces, like 10 to 15 minutes, a few of them per class lecture, and I'll also break them by topics, post them as a bunch of shorter things that you'll be able to access that way. So that's the plan, and most of all, I wanted to have at least one version of this where you can actually see my face and I'm not wearing a mask. But the hope is that these will actually be delivered live, and what you're watching will just be an adjunct to the live lectures. So what is this? Well, we're doing the second module of the Physics 100 course here at Union, which is our first year seminar. Its description you can see up here. This is some old catalog copy. It's a team-taught course, as you already know. We're introducing physics. Covers a lot of topics. All right. The not-so-secret purpose of this is to really introduce the cool stuff in physics, the stuff that's most interesting and exciting in the subject that you wouldn't necessarily get to see in the standard intro class. For this particular module, that's going to be the subject of quantum physics. I'm calling this Hot Topics in Quantum Physics. This is going to cover a lot of stuff from my own field of atomic and molecular physics. It's going to cover some laser physics, a bit about quantum measurement maybe. It's going to get into some of the issues that make quantum mechanics one of the most fascinating subjects in all of science, really. So what is quantum physics? Well, it's a very famously weird theory, right? You can Google it and you'll find all sorts of weird stuff, and they talk about issues like randomness and God playing dice with the universe. There's stuff about cats that are alive and dead at the same time, and parallel universes, and most of all material about particles that behave like waves and vice versa. Lots of weird stuff. There's lots of ways to get into this subject, but I thought for this course, I'm going to try something a little bit different. Quantum physics is a fascinating enough subject that it pretty regularly makes the news. There'll be some new experiment in quantum physics that generates some buzz. And so I'm going to frame this module around one such experiment, which is an experiment done this summer by the group of Ephraim Steinberg at the University of Toronto. And they showed that a phenomenon from quantum mechanics called tunneling takes some amount of time. And this is a groundbreaking experiment. It's really impressive what they managed to do. And they're clearing up an issue that people had a lot of questions about. So this is a really good, really neat experiment, and it also fits nicely with the sorts of things that I do in research. So makes a nice experiment to sort of frame the whole thing around. So that's the plan. So what do I mean by this? Well, here's the research article that they wrote about this. Title is Measurement of the Time Spent by a Tunneling Atom Within the Barrier Region. This is the first paragraph. It's out of the journal Nature. This is not super readable. I will put this on the Nexus site for the class, along with the two news articles that you saw in the previous slide. I'll put those up so that you can read them and get the general gist. But there's basically three things you're going to want to try to do in the course of this module. If you look at this abstract, this opening paragraph, they open with the statement that tunneling is one of the most paradigmatic and evocative phenomena of quantum physics. Right, it's sort of incumbent on me then to explain what tunneling is and why it is a characteristic quantum phenomena that's particularly important. So goal number one will be to explain that. Goal two, they say here we present a direct measurement of such a tunneling time studying Bose-condensed rubidium-87 atoms tunneling through a 1.3 micron thick optical barrier. So this is saying what they did. They took atoms, they shot them at a barrier that's about 1/100th the thickness of a human hair, and then the atoms appeared on the other side. Right? This is the tunneling phenomena. How did they get the atoms? How do they make the barrier? All of this. There's a whole lot of fascinating physics that goes into those questions. And goal number two for this module is going to be explaining how did they get the atoms that they used for this? How did they make the barrier that they used for this? How do they measure the atoms when they get to the other side? All that sort of thing. And finally, their last claim is that they localized a pseudo-magnetic field inside the barrier and used the precession of the atoms as a clock to measure the time it takes them to cross that barrier. So how did they do that? Right? This is the primary thing that they did is they measured how much time these atoms spent inside a region of space that classical physics would tell you they could never reach. And yet they do end up on the far side of it. They spend some time crossing that barrier, and they measured this using a particular technique. And the third goal of this module is going to be to explain how do they make that clock, how do they measure the time, what is it that's going on. So that's the plan. This is a way to introduce quantum physics and talk about all of these things. I'm going to explain what tunneling is, how they got the atoms and the barrier that they used for the experiment, and then how they measured the time. And this will introduce a lot of ideas from quantum mechanics. This will introduce a lot of ideas from atomic physics and optics. And hopefully all of that will give you some sense of what's really a very recent, very exciting, very new and cool paper in quantum physics research. And all of this is going to have to start with discussing the differences and similarities between particles and waves. But that's going to be the topic for the next video that I'll do. So we'll see you there.